So let's look at some examples from 4.5. And in 4.5, we're going to look at integrating where we have to make a substitution. We have a variety of rules to get antiderivatives, but not all of our functions that we need to integrate fit those rules perfectly. So we're going to look at how do we do a substitution to change them into something that we know how to get the antiderivative. For example, if we have the integral of x squared plus 4 to the 5th power times 2x dx, we might need the antiderivative of that, but we don't have a rule to integrate a product. We have rules for integrating things to powers, and we have rules to integrate things that are added together or subtracted together, but we don't have a product or a quotient rule for antiderivatives. So what we can do in this case is we can make a substitution. We can replace what's on the inside with u. So on the inside, we're going to change that to u. That's raised to the 5th power. And then the question is going to become, well, what do we do with that? So we need to translate our dx and see how is that related to du. If this variable is u, then we need our dx to change to du. So we just need to change this to a differential. If u is x squared plus 4, then du is the derivative of x squared plus 4 times dx. So if we have that, that's equivalent to du, and that's exactly what we have left. So that part we change to du. Now we have a basic power rule. So to get the antiderivative of this, it's u to the 1 larger power over that power plus c. Our original variable is x, so we need to change it back to x. So we take, in place of u, we put x squared plus 4, and that's it. Of course, if we wanted to check that, we could take the derivative as a check. So if we were taking the derivative of this, we would have to use the chain rule. The 6 on bottom, we could let that be a coefficient. So if we take the derivative of that part, we would bring the 6 down. We would do x squared plus 4 to the 1 less power. But then we would have to take the derivative of the inside. And the derivative of the inside function is 2x. And then when we take the derivative of a constant, that's just 0. So this 6 and that 6 cancel. So we're left with x squared plus 4 to the 5th times 2x, which is what we had at the beginning. So yes, what we have here, that is the correct antiderivative. So let's look at another one. Suppose we want the antiderivative of the 4th root of 5 minus 2x cubed, and we have 6x squared dx on the outside. So typically, we're going to let, if we have something an expression raised to a power or an expression under a radical, that's what we're going to replace with u. Not always, but generally, that's going to be our u, because in a sense, we're doing the chain rule backwards, so we're taking the inside function to be our u. We're trying to rewrite it as something that doesn't have to use a chain rule. So if the inside part is u, du would be, and let's change this to a positive here just to make this a little easier. Du, the derivative of 5 is 0. The derivative of this, we bring the 3 down, so that would make that 6x to the 1 less power dx. We'll just take the derivative and then put a dx on it, and that's du. So if we look at it, that whole thing is du. That part is u, so we can rewrite this as the integral of the 4th root of u du. And that's something we can integrate if we rewrite it as u to the 1/4 power. So we have our variable to a power, so we make it to the 1 greater power So what's one more than 1/4? Well, 1 is 4/4. So if we add 1 to 1/4, we get 5/4. So u to the 1 greater power over 5/4 or times the reciprocal plus c. Then to end, we want to replace u with 5 plus 2x cubed. And we could change that back to a radical if we wanted to, or we could leave that in exponential form. So that's a basic substitution, just to give us something that we know how to integrate. This one we had to make a substitution. On the first one, if we wanted to take the time and multiply this binomial out 5 times, distribute it 5 times, we could have done that and then multiplied it times 2x, and we would have had a really, really long polynomial. But just like when we were taking derivatives of something like that before we knew the chain rule, we saw how aggravating it was to multiply all that out just in order to get the derivative. So the shortcut when we were doing a derivative was to use a chain rule. So here the quote-unquote shortcut is to make a substitution to rewrite this function in terms of x to a similar function in terms of u, integrate it, and then change it back to our original variable. So let's continue working some examples. So let's look at x over the square root of 3 minus 2x squared dx. So if we continue thinking about the inside function being what we're substituting, then our inside function would be 3 minus 2x squared. So that would make du, the derivative of 3 is 0. The derivative of 2x squared is 4x dx. So we have an x, we have a dx. We're calling that u. So let's rewrite this a little bit. Let's bring the x over. So if we bring the x over here, think about that the coefficient of x is 1. So we're left with a 1 over the square root. In the end, we have an x dx. We don't have to write the 1 on bottom, but if you want to think about having a 1 on bottom, this and this are equivalent, because if you multiply straight across, 1 times x is x, square root times 1 is the square root. So those are equivalent. So if we're going to let that be u, then we need that for our du. So we have the x, we have the dx. What we don't have is the -4. Well, we can multiply this by -4 if we're clever. If we multiply by -4 and divide by -4, we're really just multiplying by 1. Anything divided by itself is 1. And as long as we're just multiplying by 1, we're not changing how much we have. The issue, though, is we don't need that -4 on bottom for our integral. So what we can do with it is we can pull it out front as a -4 on bottom. Still, if we multiply that straight across on bottom, we would still have a -4 times that square root. We would still have our -4 on top. So this makes us -1/4 the integral. Let's go ahead and make our substitution. Put the u under the square root there, and all of that is du. So if we carefully rewrite this, this may be something we can integrate. If we change this to u to the 1/2 on bottom, then we can move that to the numerator and make that u to the -1/2. Remember, when we're taking the square root of u, we change it to an exponential function. Our root goes on bottom, our power goes on top. So if we have u to the 1/2 on bottom, if we move that to the top, we just change the exponent to a negative. So this is just integrating a power. So we leave our negative 1/4 out front. We do u to the 1 bigger power. Well, 1 more than that exponent is 1/2 divided by 1/2, or instead of dividing by 1/2, we can multiply by 2/1. And then since this is an indefinite integral, make sure you put your plus c. So the 2 and the 4 reduce. So we have a negative 1/2 out front. U to the 1/2 is the square root of u. And if we replace u with our original function, u is 3 minus 2x squared. And then we have our plus c. So that one was a little bit more complicated because we had to fit it. We didn't just immediately have our du. We had to pick up an additional coefficient to make it fit. As long as we're only missing a constant, a coefficient, we can fit that. We can multiply on the inside and divide on the outside by the number we need to change to transform it. Where we run into issues, though, is if we're missing a letter on the inside. If we needed an x squared here instead of an x, we can't pick up an x on the inside and divide by an x on the outside because we can't put a variable on the outside. We can put constants on the outside, but we can't put variables that are the same variable of our integral. So let's go on and do another one. Let's suppose we have dy over dx equals 12 x squared over the square root of 7 plus x cubed. And we want to find a general solution for this differential equation. So essentially we're looking for what is y. This is called a differential equation because our equation has differentials in it. So there's an entire class on solving differential equations. But if we're given the derivative and we want to find what function has that derivative, we just are basically looking for the antiderivative in this case. So if we move the dx over, we have dy equals 12x squared over the square root times dx, so we're just changing it to the differential form. And then to get y, we're going to integrate both sides. Now, you might say, well, if it's just that simple, why is there a whole class? This is the most simple type. There are differential equations that are way more complicated that we can't just simply isolate our variables and get the antiderivatives for. All right, so on the left side, if we have just dy or 1 dy, when we integrate the constant, we pick up our variable. On the right side, we're going to have to do a substitution. Now you might say on the left side, why is that not plus c? Well, we could put a plus c here, and when we integrate this, put plus a different constant. But when we solve for y and we combine our constants, one unknown constant minus another unknown constant is just an unknown constant. So when we collect our unknown constants from both sides, we just have some unknown constant on one side. Okay, so if we come back here, our inside function is 7 plus x cubed. So our differential du is the derivative of that, which is 3x squared times dx. We'll notice we have 12x squared dx. We only need 3x squared dx. So different ways to fix this, but let's do this. Let's begin by pulling the 12 out front, since that's more than what we need. And let's move our x squared over with our dx. So if we move the 12 out front, the understood coefficient that we're left with there is a 1. And then put the x squared there. And then leave our square root on bottom. So we need 3 times x squared. We have 1 times x squared. So to fix that, multiply x squared times 3 and then divide by 3. Notice all of this is a product, so we don't have to put our divided by 3 here. We could put it here, 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 as long as this is all multiplied together. So y equals 4 times the integral. This whole thing becomes du. Just like on the last problem, we have a square root of u on bottom. If we move that to the numerator, that's u to the negative 1/2. Because that's u to the 1/2 on bottom. Move that to the top, it changes that to a negative. So if we get the antiderivative here, and that is 4 times whatever we get for our result. So when we integrate this, it's u to the 1 larger power over 1/2, or times 2, plus c. 4 times 2 is 8, u to the 1/2, or the square root of u, plus 4 times c. Well, 4 times a constant, if I multiply a constant times a constant, we still have a constant. So the only thing left to do is to replace u with what we put u in place of. So u is equivalent to 7 plus x cubed. So that's the solution to our differential equation. This is the function whose derivative is that. And if you wanted to check that, you could take our function, you could take the derivative of it, and see if that gave us what we had to start with. All right, let's do the integral of, let's say, x squared minus 3x to the 4th dx. And out front, actually, let's make this, instead of 3x, let's make it 2x. And out front, let's call it x minus 1. So we have a couple choices on what we're going to pick for our u. We have something in parentheses here, something in parentheses here. If we have parentheses 2 different places, we're often going to pick what's the one of the higher degree. If we look at picking this one, then when we take the derivative, our degrees are going to get smaller. If we let this one be u, then when we took our derivative and we got a smaller degree, this one is bigger than that one. So if we take the derivative, we're getting farther away from that degree. Where on the other hand, if we pick the bigger one, when we take the derivative, we get 2x minus 2 dx. Notice the degree goes down by 1, and that's what this is. Each of these terms, if we go down a degree, we get the corresponding term. This degree is 2, this one is 1. This degree is 1, this one is 0. So pick the higher degree polynomial for u, and hopefully our du will be either this or closely related to that. Now notice these two don't match. But what we can do is notice this differential is factorable. Both of those have a 2 in common, so we can factor a 2 out. So the only thing we're missing, if this is going to be u, and we need that to be du, we have our x minus 1 dx, we just need a 2. So we can multiply by 2, and we can put a 2 on bottom out front. So we could make a substitution, and 2 times x minus 1 times dx, all of that is du. That is u to the 4th. So to integrate it, we leave our coefficient. We do u to the 1 bigger power over that power. or we can put a 1/5 out front, plus c. So 1/2 times 1/5 is 1/10. U is x squared minus 2x. That's to the 5th power, and then we have our plus c. So the biggest thing here is making a substitution and then making whatever is left fit our du. So let's do one more indefinite integral. Let's do one where we have cosine 2x squared times sine 2x dx. And actually, I want to, well, yeah, that's fine, that's fine. So if we look, our inside function is cosine 2x. The derivative of that, or the differential, the derivative of cosine is minus sine times the derivative of the inside function, dx. Don't forget the dx on the end because this is a differential. So du, if we rearrange this, we can put the 2 out front. That's negative 2 sine 2x times dx. So we have a sine 2x dx, but we need a negative 2 with it. So we can multiply. We're not subtracting, we're multiplying by negative 2. And if we multiply by negative 2, we also have to divide by negative 2. So essentially, those cancel each other out. But by doing this, that's going to be u squared. That's going to be our du. So we have negative 1/2 times the integral of u squared du. So negative 1/2 u to the 3rd over 3 plus c. So we get negative 1/6 u is cosine 2x, and that's cubed. So just picking the correct thing to be u. It's not always obvious what you need to pick for u, so pick something, and if what's left does not remotely resemble du, then throw out your u and try something else. Okay, let's do a definite integral. Let's look at the integral that goes from 0 to 1. Let's do x squared times, let's do 4x cubed plus 2 to the 5th dx. So let's make a comment. These values, this is an x value, this is an x value. If we looked at this function, this function goes from an x value of 0 over to an x value of 1. So we have some curve, and we're going from 0 to 1 in the x direction. So if we change our variables on the inside to u variables, then these numbers may not be 0 and 1 when we change to u. So we have two options. Option 1 is to get the antiderivative. In terms of x. So we may have to do a substitution, get the antiderivative and change it back to x, and then plug in the 1, plug in the 0. So we have to change, we'd have to make a substitution. After we get the antiderivative, then we would change back to x, and then we would plug in a 1, we'd plug in a 0. And that's fine, there's nothing wrong with that. The second method we could use is in the process of getting the antiderivative, we can change our limits. Instead of from being x values, we can change them to u values. And then we have some function of u. So when we get the antiderivative, that antiderivative is a function of u. So we can plug in u values to the antiderivative. So we've done a complete transformation. So it just depends on which way you prefer to do it. So I'm going to do it each way just to show you what I'm talking about. So we need to begin by making a substitution. So that's our inside function. So we're going to replace 4x cubed plus 2 with u. So what would that make du? So it's the derivative of u times dx. So notice this and that's almost du. That gets our x squared and our dx. We just need to multiply the x squared by 12. So if we multiply by 12 there, we can divide by 12 on the outside. So we can call this 1/12 the integral of this part is u to the fifth. This and that are du. So if I'm going to change it back to x's, I'm not going to change these numbers, but I'm not going to write a 0 here and a 1 here, because this 0 is an x. When I change to u variables, a 0 in the x is not a 0 in u. So that's changed. So we can, if we want to, just get the antiderivative of our function and then plug in a 0 and a 1. And when I say the antiderivative in terms of x. So let's see how that would look. So we would integrate this, u to the 6th power over 6. Since we're doing a definite integral, we don't have to put the plus c on the end. So we would have 1 over 72. U is 4x cubed plus 2 to the 6th power. And then we would evaluate that from 0 to 1. So we would plug a 1 in. We have a 1 over 72 out front. If we plug a 1 in, we get 1 times 4. So 4 plus 2 to the 6th power. And then we would subtract 1 over 72 times plug a 0 in. 0 cubed is 0. That 0 plus 2 is 2 to the 6th power. And then we would just simplify that. Ideally, it'd be good to do that as a fraction, but we could do it as a decimal also. I'm going to factor the 1 over 72 out. And that's going to leave us 6 to the 6th power. 6 raised to the 6th power. Minus 2 raised to the 6th power. Times 1 over 72. So if we take 46, 656, subtract 64, we get that, 46,592, times 1 over 72 or over 72. Now, it'd be great to reduce that, of course. I doubt that's divisible by 72, and it's not. So we could reduce it by 2. So take that, divide the top by 2, 23,296. Divide the bottom by 2, we get 36. If we divide the top by 2 again, we get 11,648. Divide the bottom by 2, we get 18. Divide them both by 2 again, we get 5,824. Not 924. 5,824. We get 9 on bottom. And Does that divide by 3? No. So that doesn't reduce anymore, so that's completely reduced. So real quickly, what we did, we got the antiderivative in terms of x. We integrated it, we got the indefinite integral in terms of x, and then we plugged a 1 in and we plugged a 0 in. So that's great. There's nothing wrong with doing that. Let's do it the other way. So our original problem, we're integrating from 0 to 1, x squared times 4x cubed plus 2 to the 5th dx. So this time, instead of changing from x to u and then having to go back to x because these are x values, let's change everything to u and then leave it in terms of u to get our answer. So our substitution is going to come out the same. The u is what's on the inside, which makes du still 12x squared dx. We're still going to multiply by 12 and divide by 12. So we're going to have a 1/12 out front. 12x squared dx is still du. We still have u to the 5th. What's different is that we're going to change an x value of 0 to a corresponding u value. Well, how are we going to do that? Well, we have this relationship right here that tells us how x and u are connected. If x is 0, then u is 4 times 0 cubed plus 2. So when x is 0, that corresponds to u being 2. So we would put a 2 here. When x is 1, we need to find out what u corresponds to that. So we would take our relationship. When x is 1, 1 cubed is 1. 1 times 4 is 4, plus 2 is 6. So when x is 1, that corresponds to u being 6. So now, get the antiderivative. 1/12 times u to the 6th over 6. And instead of changing it back to x and plugging in 0 and 1, we just plug in a 2 and a 6. So we have 1 over 72. We do u, so we plug a 6 in, and we have 6 to the 6th. We plug a 2 in, we have 2 to the 6th. And that's exactly what we did in our calculation over here. 1 over 72, 6 to the 6th, and 2 to the 6 to the 6th, and 2 to the 6th. So we end up with the exact same answer. It's just a matter of, do we want to take the time to find out what these individual x values convert to if we're converting everything to u, or do we want to skip that step and when we get the antiderivative, change it back to x's so we can use those numbers? End up in the same place. It's just a matter of which way we want to go. All right, let's do one like this. Let's suppose we have x squared plus 3x to the 4th over the cube root of x dx. So if we try to make a substitution and let the inside part be u, that's not going to really get us anywhere. Those are essentially just different letters. This is u to the 1st, that's x to the 1st. The derivative of x is 1 times dx. So if we try to replace every x with a u and dx with du, nothing is going to look different except we're just going to have different letters. Nothing is going to be more simple. So that's not going to be what we want to do. That's not going to work. If we pick our largest degree, then that doesn't really get us anywhere. Because couple reasons. This is added. If this was times and that was x cubed, we might be able to make it something times du. But being added and plus that not being x cubed, that doesn't really get us anywhere. But we can do some algebra here. A couple things. When we only have one term on bottom, it's not too terrible to divide this fraction into two different fractions by putting x squared over that denominator and 3x to the fourth over that denominator. Now when I put it over that denominator, I'm going to go ahead and call that x to the 1/3. The reason for that, since both of these have base x, when we divide, we subtract the exponents. So when we subtract these exponents, 2 minus 1/3, to subtract those, we have to have a common denominator. So multiply by 3, multiply by 3, so we have 6/3 minus 1/3. So when we simplify that, that's x to the 5/3. Then we have plus 3 times, subtract those exponents. The bases are the same, so when we divide that, do 4 minus 1/3, and that'll tell us how many x's we have left. So common denominator again is 3. So we have 12/3 minus 1/3, so that would be x to the 11/3. Now each term is just a power rule, x to a power. Notice it's not a definite integral, so we're not plugging any numbers in after we integrate. So power rule, we do x to the 1 bigger power. If we add 1 to this exponent, we would be adding 1 or 3/3. If we add 3/3 to that, that would be 8/3 over 8/3 plus 3 times. If we do this x to the 1 bigger power, we would be adding 1. Or if we're adding 1, we're adding 3/3. So that would be x to the 14/3 over 14/3, then plus c. So it'll end up with 3/8 x to the 8/3 plus 3 times 3 is 9. 1 times 14 is 14. X to the 14/3 plus c. And we could technically factor out what they have in common if we wanted to. They both have at least x to the 8/3 in them. So if we factor out x to the 8/3, we have a 3/8 plus 9/14. If we take 8/3 out of this, remember if we're factoring it out, we're essentially dividing it out. So if we have x to the 14/3 and we're dividing out 8/3, when we subtract those exponents, 14 minus 8 would be 6/3, so we'd have x squared left there. So I'm fine with you leaving it that way, or you could rewrite it that way. You could also pull a 3 out on top, pull a 2 out on bottom. If we did that, we pull out the 3 out there, we're left with a 1 on top. If we take a 2 out there, we're left with a 4. If we take a 3 out there, we have a 3 and a 7, x squared plus 6. There might be terms where that's beneficial, but this is just good enough.